Hi, in this bench tip video I'll be showing you how to determine the ratio of transformers, a quick and easy way. It's a bit rough, but it works. It gives you an idea of what to expect with the voltage coming out, and yeah, basically all you need is a way of creating a waveform, preferably a sine wave, but I'm sure you could do it with some audio equipment, and you need an oscilloscope to do it with. Okay, so let's go to the bench and have a look. Right, before we actually go to the oscilloscope probing and stuff, we should actually determine our windings. I should have mentioned in the intro we also need a test meter or some kind of continuity meter. Something that beeps is better. And basically I'm drawing a quick diagram of the pinouts. Now, if you can, before you take your transformers out of a circuit, it's probably be nice to actually see the circuit board beforehand. I did, however, on this, but I'm going to do it just as an example. Okay, so what I like to do, this looks like the primary. Well, I know it's the primary, but you can see the bigger leads usually signifies a primary. Right. I measure 168 ohms across there. Nothing across there. Nothing across there. So that's a no connection, and that's the primary winding. Okay, now there's a low resistance there, so that must be unwinding. Is this not connected to any of the others? No. Okay. Okay, these have low values winding, so let's is how we determine, see if we can find which is the center tap. Okay, so that's 2.1 ohms between these 2.1 ohms. Across the whole thing is clipped it on. Okay, across the whole thing is 4.2 ohms. Okay, now across these two. 2.3 ohms. As you can see, the resistance of these two combined, so therefore, and the resistance across there and there is the highest, so therefore that must be where the center tap is. So now we'll get ready to set up and measure the windings with signals. Okay, what I've done here is it's not connected to this yet. I've just connected to the oscilloscope. Now, as you can see, I've got almost a 60 Hertz wave. It's 6 volts peak to peak. Input is what's going to go in there. So 65, 6 VPP. 60 Hertz is going in, and then what we're going to do is we're going to measure all the windings and see what goes on. So I'm going to hook up the bottom set of windings and then we'll come back. Okay, so I've hooked up this here, and I've put it on the scope here, if it can focus. Okay, it's measuring here 6 volts peak to peak in, and out, I don't know if you can see it very well, but we're getting 8.24 millivolts peak to peak out. 8.24 millivolts peak to peak out. And that is in phase. Okay, now this is a step down, so we do expect that. Okay, so let's measure the next lot. Now, what I'll do is to move this over here. Okay. Okay, so across the entirety of it, see what it's receiving. Let's say 5.7, say 570 millivolts peak to peak. Okay, and let's try it across the one winding. I'm getting, come on, focus. It's about 295. Okay, and I shouldn't probably get the same at the top. Don't worry about it being out of phase, it's just the way I've hooked it up. So yeah, we're getting similar across the top. So this is the output for this transformer. Okay, I'll unhook everything and then we'll come back and do the calculations. Okay, I did some calculations on the numbers. Basically, I took the input voltage divided by the output voltage to work out the ratios. Now, these are the ratios for the windings. This is for the across the put the center tap, one with the center tap across there, and this one, since they both seem to be identical windings, I just worked out for the one winding. And as you can see, the relationship between these two almost proves it. So, but let's take it another step further. Okay, let's work out the volts peak to peak voltage for each of the output lines. Now, the mains voltage here in Canada is 120 volts RMS. So we're going to convert this to a to a peak value. So we divide it by 1.414. Then now we're going to convert it to a peak to peak value by multiplying it by 2. So we get 169.7 volts peak to peak. And now we work out the scaling for our tests. So we divide this number by the input for our test, which is 6 volts peak to peak. So we divide that by that. So therefore, our tests are 28.28 times smaller than the real values if we were plugging it into the mains. So then I worked it out for these individual results we got on the other page. Now, if we want to prove these results and prove the ratios we got, all we have to do is take this number here and multiply it by the ratio of that winding. So multiply that by 7.28. Okay, so that's 23.3 multiplied by 7.28, If this equals this number here, then we know it's correct. Pretty close. So let's try this one. So that's 16.12 multiplied by 10.53. There again. That's a bit more accurate. Okay, what I've done here is I've made a list of the output voltages, and I've converted them to RMS voltages.
20.
If we hooked up the transformer to the mains,
there it is again.
120 volts RMS.
So that shows this is working.
Those are the values we'll be getting out, and they all look pretty decent to me. And yeah, they look like some useful voltages there. But that's how you can estimate the voltages coming out of a transformer using some kind of function generator, an oscilloscope, and a test meter. So there we have it. Simple method of calculating the ratios and the estimated output voltages of transformers. There may be a step in there, a skip that could make it easier by by using the ratio to divide to work it out. But we could go through that and it would prove the numbers to be the same anyway. I hope that was useful to you, and thanks. See you again for another bench tip. Goodbye.